Hello, welcome to problem help with Unit 1, Lesson 4 projectile motion. I'm looking at question number 35. So we have a soccer ball is kicked from the ground. So I'm going to give myself a bit of a drawing. I always like a drawing to kind of help me visualize what's going on. So it's kicked at an angle theta. So there's my theta. And we want to prove, so this is a prove question, that the height show that the represents maximum height of the ball. So we are looking for, here's the maximum height. So that is going to be our h. We got the theta and the range. It's from start till finish, so that's our r. So our goal is to prove that 0.25 r tan theta is our maximum height. So it's a projectile motion question, so I'm going to break it into horizontal and vertical. So horizontal, we know that delta D, it's an unknown. I really don't have, well, that's not really true. I do know some information. The key point in time here that we're looking at is halfway through the path. So right here, so that means our distance to the halfway point is going to be half the total range. So delta D will equal 1/2 the total range that we can kick it. Our velocity is going to be the magnitude with which we kicked it, cos theta, and our time, that is not known at this point. So the only equation for horizontal that we have is delta D equals VT. Substituting in what I have, 1/2 the range equals the magnitude of V cos theta T. All right. Now, kind of looking ahead, if we go back to showing what we're trying to prove here, we can see that time is not involved. So that means that I'm going to be substituting to get rid of time. So I'm going to take the question on this side one step further and isolate for time. So that means I would end up with range on top and on the bottom 2 multiplied by the magnitude of velocity cos theta equals time. All right, so that is where I'm going to stop with my horizontal. So let's analyze our vertical and see what comes from that. So our vertical delta D, well, that's represented with h, the height. My initial velocity, so that's the magnitude of v sine theta. And this is going to be up. And meters per second, I've kind of dropped my units here. But since it's a proof, it's not quite as important. What else do we know? We know acceleration. I'm going to use 10. So 10 meters per second squared down. And I'm going to have to substitute t in, so I'm going to use t on that side. So now I go to my equations and I try to pick one that is appropriate. Oh, another piece of information I know is V2 is 0. At the peak, or at maximum height, right here, it stops moving upward and transitions to downward. So for a split second, V2 is 0. So that's a nice thing because I like when V2 is 0. So I have to use V1. I have to use, or want to use V2 because it's a 0. I have to use D, and I have to use the time because we're going to plug the time in for that. So I need to pick an equation that has all of those. So looking at the formula sheet, I'm going to go with delta D equals 1/2 T V1 plus V2. Doing our substitution then with what we know. 1/2, now I'm going to replace T with all that information. R, 2 multiplied by velocity, cos theta. V1 is the magnitude of V sine theta plus 0. All right, not the neatest, but still managed to read that. Magnitude of V's will cancel. And what are we left with? Height equals, on top, I've got an R. I have cos in my denominator, sine on top, so that becomes tan theta. On the denominator, I have 1/2 times 2 down there, so it's 4. So H equals 1/4 R tan theta, or to match up with what the book has asked, 0.25 R tan theta. There we go. We have successfully shown that the maximum height, is connected to your range and the angle of launch. Can you expect a question like this on a test or exam? I would say yes, about that difficulty. And keep in mind, you're just substituting one equation into another and playing around with the equations. So if you have any questions or follow-up questions, let me know, and I will answer them as best I can. Good luck.